I'm a senior .NET developer and a Microsoft MVP on developer technologies. You already know when talking about AI, data is the most important thing, and IoT has this data. In machine learning, data has to be labeled for the most of the scenarios, but labeling is not easy and it's not cheap. Most of the time, the data is raw data, either if you take it from Excel or CSV files or from a data lake, and it's not labeled. So we still have to do this labeling ourselves. In today's talk, I will present a proof of concept which won the third place at the virtual ML hackathon a few months ago. So I will mix together the power of IoT with the power of AI in order to automate the data labeling. More specifically, I will use a Raspberry Pi, which reads some sensors data, and it has a camera attached to it. It's broadcasting the images to the client, to us. Actually, it's the main module which is doing the prediction. It's identifying, it's recognizing images, and it's doing the predictions. So let's get started. Traditional programming is all about having input data, applying some rules on that data, and getting the output. We are so used to this, we don't even realize it. So take a look at these pictures. In the first picture, we see many people planning, processing, using their brain 8 hours per day to do their work. In the second picture, we see the evolution. Many people, let's say developers, planning, processing, using their brain 8 hours per day to do their work. In a particular way, we train these people to be developers. Indeed, it is a revolution, an evolution actually. And we put our intelligence or our algorithms in machine code. And that code is running on our machines, and they are doing our work. On the other hand, with machine learning, data goes in and the learned rules come out. And comparing to classic code, we can say the machine learning model is alive. It's a live code. Your code is not. And because your code is not adapting itself, you have to maintain it. Every single little change you want to do, you have to code, you have to debug, you have to test, and it's not adapting itself. So let's put this simple or simpler. With every build, your code is frozen into binaries. So what not to put the machines to create these algorithms or intelligence? Let's look at these pictures. The second one may look scary, but by using AI, I mean machine learning and deep learning, we have the chance to see a new evolution. So where are all the people from the first picture? Well, maybe having piña colada on the beach. I'm sorry, guys, we still have COVID-19 around, so let's wait a little bit more for piña colada. And now let's get serious again. I have an interesting hypothesis for you. Has machine learning more human-like behavior than traditional coding? Actually, yes. And let me give you a simple example. Writing algorithm, it's like writing a cooking recipe. A recipe has ingredients and steps you have to follow in order to get an eatable food. But you did the recipe before, and the machine is only executing it. So is the machine intelligent for running your recipe? Is this making the machine more human? No. On the other side, failing and succeeding and repeating until the recipe is good to eat, well, this is making the machine more human than coding. We, as developers, have to be prepared for this new paradigm, I mean, machine learning, because in 10 or 20 years, it will change the way we code. But until then, we continue to write our own recipes. Look at the first picture again. We have the machines, but we are still doing the hardest part here. Hundreds of millions of developers are writing cooking recipes, and the machines are just blindly running them. So this will change soon. When I first had to deal with machine learning, I believed that finding the right trainer is the hardest part, and it was totally wrong. Let me make a disclaimer now. I'm not a data scientist, I'm a developer. But of course, I'm trying to nail down the role of data science. From the development perspective, the hardest part is to get the data ready for building the machine learning model. And to find the right trainer, we can make use of tools like Model Builder, which is Automate ML. And what's the idea? The Model Builder is able to detect which is the best trainer from a catalog of trainers for your scenario. And for your scenario, yes, but training a model and measuring its quality in a given time frame. The best model wins. Maybe you don't need the best in terms of accuracy. Maybe you need the fastest or something in the middle, but nevertheless, you have a suggestion of which are your models. Now, don't get me wrong, I'm not saying a data scientist is not needed anymore. What I'm saying, you don't have to be a data scientist to get it started. So let's state a few things. Your machine learning model cannot be better than your data set. Take care on your data. Even more, it's more important to have a good data set than having the smartest algorithm. Because a bad data set simply will result in a bad machine learning model. Take care, bad data doesn't mean only erroneous data. Bad data can be highly biased data as well. So if you decide to save some time by skipping data preparation, do not be surprised if you have to pay the price later. You will waste a lot of time and not in a productive way. So, are you familiar with the technical debt? I hope you are, because the similarities with the technical debt, I will call this data preparation debt. But first things first, loading the data. We have some observations which we acquired from the IoT device, which is a collection of lines consisting of features or readings. The supervised learning needs a special feature which serves as target feature or label. And tagging an observation with a label is called labeling. My use case used for the demo is supervised learning, more specifically, it's multiclassification. Therefore, my label will be a category or a class. Binary classification and regression, the same, they have a label because this is specific to supervised learning. But as I said, we will focus on a multi-classification scenario. So the word supervised for multi-classification comes from the fact that the observations are labeled. Let's take a look on the anatomy of our data. Let's suppose we have a system able to read some data from an IoT device, like temperature, luminosity, infrared, distance, and the created daytime. And we have a data set consisting of about 1,000 observations or lines or readings. By the way, how much data is enough? Well, this comes with the experience, but keep in mind, if you have more categories or classes, you need more data. And if you need more precision, again, you need more data. Too much data never hurts, as long as it's good data. So these observations are labeled, and we have a feature called source for these readings, for every observation in the dataset. In fact, the source which stays in the front of the sensors is generating these observations. So somehow we have a mechanism to pre-label our observations, our data from the sensors. So these sources for our scenario are a lighter, a flashlight, an infrared, and simply the daylight. The daylight is like a catch-all for anything but those classes which I mentioned before. So if the first three sources are easy to guess, this one is special. And this is the default category, as I said. Let me exemplify. We have a data set with readings from an IoT device, and we want to predict the source of these readings. So giving 20 Celsius degrees and 90% luminosity, 0 infrared, and 50 centimeters distance from the source, well, that's like a cold light. It's not giving heat. And very probably we are talking about a flashlight, not a lighter, not an infrared, and it's not the daylight because we have something already there. So let me tell you, it's important to understand what problem do we solve. Actually, I realize maybe this is the most and the hardest part when dealing with machine learning, to understand the problem. Because machine learning is not a universal panacea. You have to identify where is better to use machine learning. I see machine learning like a complementary skill to traditional programming. It's not replacing traditional programming. So our use case is multiclassification, but depending on the label or target feature we choose, we can have binary classification or regression. Look at the table and imagine a classical approach consisting by classical approach, I mean traditional programming, which is consisting of a huge tree of if and else to model all the cases for this data from our sensors. So therefore, we might end up having here, for example, we have 4 features from 4 kind of sensors. So for this, if we combine this, we might end up having 2 by 4 if-else statements, and that's 16. But what about if we want to add another 3 features? I mean, that's 7. Well, that's 2 by 7, which is with 128 if-else potential branches. And think about the thresholds you have to adjust manually for each of these values in order to decide if a value is big enough or small enough to be part of a lighter or of a flashlight. You got the point. It's getting quickly towards a large chaos. So bad news, you did all the work indoor, and now let's move the device with all the sensors outdoor, and your code will simply fail because the system is not calibrated to work outdoor, and you have to redefine all the thresholds and maybe even change the algorithm in a few places. So you can realize this is not adaptable at all. So this is the classical approach. But to do all of these with machine learning, well, it's like poetry. So you know what? The more features you have, the better to use machine learning, because our brain is simply not built to identify large dimensional analytical data. Actually, take a look at this picture. Our brain seems to be much more adapted for images. We have already some instruments to see information like images or sounds or video, not analytical sequence of bytes. Even if there are involved more than 7 features, our brain performs better because it's trained for an entire lifetime to recognize such objects. So we can say our brain has its own model. Actually, it has a lot of models. And the brain is connected to its own sensors and camera, eyes, ears, and so on. By the way, there is a recent job for doing this. I mean, labeling images. I think my headset will, the battery, it's done, is dead. So I will try to deal with this, but just give me a few seconds so I can switch on the speakers in case we need to talk again. So I will continue. By the way, so you can see now this is live. Yeah, it's a proof. When you have technical issues, it's cool. You're getting alive. So by the way, this job, labeling images, there are companies offering image labeling services where people are labeling shapes in pictures all day long. So funny, 2021, and we are doing most of the image labeling by humans. We have cheap IoT devices and sensors. We have performant image recognition algorithms. Maybe the most performant is more than 99 accuracy, but we are still labeling data using humans. Let's get back to our analytical data. So where humans seem to perform worse. So who's labeling the analytical data? This is the question. Let's take a look on this time axis. The past is the past. We cannot do much with the data in the past. But for the present and for the near present and for the future, we can do a lot if we have something with good eyes and good ears. And I'm talking about computer vision, of course. Let's put the deep learning to work. So the plan is to use deep learning to get the data sets labeled. The way we can actually then with the obtained data sets, we can train machine learning models. No, this is the problem. We need data, and we need good data, labeled data. And now we are getting to 2021. Indeed, an IoT device has better eyes and ears and much more senses which humans simply does not possess. We can train a deep learning model to recognize a precise set of categories. We as humans are able to detect anything. If you are trying to detect our four sources, if a bee flies in the front of camera, we are detecting the bee, but you know, it's not relevant for our use case maybe. So we can train a deep learning model, a highly performant deep learning model, to recognize a precise set of categories. For example, our categories: flashlight, lighter, infrared, and the daylight. We do that one time, and we are expecting to perform better than humans in the most of the tasks. Oh, and opposing to humans, it doesn't get tired and it doesn't fail. We have a tendency to evaluate the human skills at their best shape. But what about bad days? What about fatigue or stress? I don't want to think about. So what we get here, an automate labeling system which needs very little human intervention, and it's more like supervising, but supervising is much better than doing all the work. So isn't this great? Now you can bring the piña colada. So I said we cannot do much with the data in the past, but if we are lucky, for already existing data sets, we already have a good candidate for our label. But most of the time we don't have a good candidate for the label. So we will address those situations when we don't have a good candidate for a label. For the near past, we can do the pre-labeling. Well, pre-labeling does not involve deep learning, but it deserves mentioning it because it's a very good technique to get the data sets labeled. And for smart labeling, which is real-time labeling, and for the post-labeling as well, with the help of computer vision, we are safe. We can do the labeling, not ourselves, but our deep learning model. Of course, IoT will play a critical role in our scenario. Actually, IoT will play a critical role in artificial general intelligence. Actually, I cannot imagine artificial general intelligence without IoT. I like very much SAS, which is an important company which does statistics and services. They are associating AI with IoT in IAoT. That's very, it's like a fusion, natural fusion, the next step. So we can use IoT devices with sensors and computer vision to replace humans in many areas of dataset labeling. I'm talking about machine learning analytical dataset labeling. So in fact, we put a deep learning model to the supervising, to do the supervising instead of humans. I'm trying to make sure it's everything all right. I will continue.
It's all good, Daniel.
Thank you for the feedback. Now I'm cool because I know you can hear me. So for the demo, I have used cheap resources like a Raspberry Pi. You know already, this is about the recommended price. It's $35 US. And I have a camera. This is even cheaper, and very cheap sensors, a couple of dollars each, or some. For example, we have luminosity sensors, which is a brick sensor. It's analog, but in order to use it with the Raspberry Pi, I have used analog to digital converter, because Raspberry Pi works with digital signals. And this is not calibrated, and that means we have to interpret the data on a scale, but temperature on the other side is calibrated. And in addition, we have ultrasonic sensor, which is digital, so we don't have to convert anything, and it's calibrated as well. So as you can see, we have different kind of sensors. And we have our categories, which we are trying to detect, and that's again flashlight, lighter, infrared torch, or daylight. So again, if it's not clear enough, I will have this system which is powered by a Raspberry Pi, and it has all these sensors, and I will put in front of the sensors one of these objects, a flashlight or a lighter or an infrared torch, or I will simply leave it alone, and that's daylight. But yeah, so a few words about deep learning. TensorFlow is an open source framework for deep learning and machine learning as well, with support for many languages, including C#. And if you plan to build and or train deep learning model, you can use TensorFlow.net, for example. I'm addressing specifically .NET developers when I'm saying that. Of course, it takes some time learning it, and you need some data science skills. But what about if you don't have either of them? I mean, time and data science skills. Well, remember, we want to use TensorFlow pre-trained models in our C# code without the need to learn Python. Currently, ML.NET is helping us with that. For now, for deep learning, it's limited to predictions and transfer learning. So you cannot train from scratch a TensorFlow model in ML.NET, but you can do the transfer learning, exactly what we need. Transfer learning, it's actually retraining a small part of our model. We can get TensorFlow models trained with other frameworks, and we just consume it in ML.NET. But nevertheless, training a deep learning model from scratch may take several days or even weeks, depending on the computing power. Inception model is our model for image recognition. For demo, I have used Inception version 3, which is a pre-trained model able to classify images in 1,000 categories, like animals, plants, different objects. So you can train for new classes using transfer learning, but for a smaller subset. As I said before, we need to identify 4 classes: flashlight, lighter, infrared torch, and daylight. So these are only 4. We don't need the original 1,000. And for that, we will use the transfer learning to borrow the powers of the Inception model, but to retrain it for our needs. So as I said, transfer learning is about retraining for a smaller subset, not necessarily smaller. Obviously, for us, it's smaller. And the inception model consists of two parts. It's feature extraction and its classification. Let's see. Let's take a look on this image. The first part up to this red arrow, it's the feature extraction part. And only the little dot, the little blue dot, it's classification part. So we have zoomed in this, and we plan to retrain only this part. This is the part we need to retrain for our smaller subset, which are our classes. Inception model is able to detect small, in the first phase, small shapes, lines, edges, corners, shadows, and then in the next layers, it's able to detect larger shapes like a leaf or a nose or a wheel. And then we need these muscles to train it with our objects, which is, again, the lighter, the flashlight, the infrared torch. Let's take a look. Let's go further and take a look on this wonderful tool. Neutron, it's a tool which allows us to inspect the layers of a deep learning model. And of course, the question is how I can identify the layers for the model. Which, well, do not expect to figure out alone this only from the picture. You have to read about the model, maybe the white paper, or you have to get familiarized with the model, and then you can identify which layers are those which we need to change, or yes, or to adapt. Let's observe the softmax layer at the bottom of this image. Classifying a new image using the original model will get one class in the 1000 classes. But again, this is not what we need. First, because the classes for lighter or flashlight or such classes, they might exist, but they are not trained with the same images which are better for us. So it's better to train your model with the images from your scenario. Of course, and we need to limit the classes to our categories. Now, this is a sample consuming the inception model in order to classify for originally 1000 classes. As you can see, we don't load new data. We have already the model. We just initialize the data view object with an empty list. What we need this empty list? Because we need to read the schema of our data, the header. So further, we are building the processing pipeline. As we can see, we are loading the image we want to predict. Then we are resizing the image, and then we are extracting the pixels in order to get the analytical data. And then we load the TensorFlow model. The TensorFlow model is instructed to run from the input layer to the softmax2 layer. And then we call .fit method in order to get everything trained. After this point, we have the model and we can start to make predictions. How we are doing that? By creating a prediction engine and calling .predict method with the new image. What we get on the other side, it's a prediction. But as I said, this is predicting one class in 1000 potential classes. We don't need exactly this. What we need we need to stop earlier in the softmax underscore pre underscore activation. Let me show you back the image. So we are not stopping at the end at the softmax layer. We are stopping right before the classification, because up to this point we have the muscles of our deep learning model, but then we have to take control and classify in our 4 classes. Let's go back to the code. So we stop earlier, but then we call a trainer which does some multi-classification. For example, it can be this trainer. It's LBFGS. Don't ask me about the abbreviation. I didn't memorize, but it's doing multi-classification. And after that, we are able to predict in our 4 classes exactly what we need. Let's see it side by side. So in our first scenario, this is the right part, is the original code, which is predicting for 1000 classes. We are calling everything with an empty list because we need it only for the schema. But in the left part where we used our model to retrain, we need to inject, to drop in the model some new data. These are our new images for each category. Let's assume we have 50 or 20 image for each of these category: lighter, flashlight, infrared. Well, by loading this data, building the same pipeline mostly, stopping at the softmax 2 pre-activation and doing the classification ourselves, we are getting a model able to predict in our subset of the classes exactly what we need. So, okay, I missed to show you this, but now it's more visible. So this is what we have to change. Of course, we have to add the classification trainer. In our demo, we have 2 IoT devices, but we can scale up to as many as we want. I mean, for my scenario, I have used one IoT device where I'm doing the computer vision. So I have a camera attached to it. And I have another IoT device where I'm doing the second one here, where I'm doing the sensors reading. We can imagine having multiple cameras, which is great because we can see from different angles. But for a proof of concept, it's good enough. But for something serious, we need to be able to see the image from different angles. And of course, we can aggregate the information from multiple cameras. So for now, the IoT devices are responsible only for data acquisition. Usually, this is how we can use an IoT device. Sometimes we can do some processing on the IoT device, but as now, this is a work in progress for ML.NET. Hopefully in a few months we will be able to do machine learning on IoT devices. So what I'm doing, again, I'm reading from the IoT devices in a centralized place where is my server and where I'm doing the predictions on my laptop. Let's get to demo. I have pre-recorded the demo because, trust me, it's not easy to present and to turn on some lighters and take care on the sensors. It's a proof of concept and it's pretty unstable. So I will use my pre-recorded video for doing this, but I will explain. So this is the application. In the left part, we have the module which runs on my laptop. In the right part, we have the interfaces from the Raspberry Pi devices. Take a look on the background. I put the picture in order to make it more clearer. So I'm reading data from the sensors. I have an interface, an HTTP interface for this, a web interface. In this application, I'm reading the data from the sensors. In the second application, I'm reading the data from the camera. Then I'm pushing real time this information in the left part to the application which runs on my laptop. There we are doing the magic. I mean, first we are sending the data from the sensors, and second, but in the same time, we are sending the captured images from the camera. The deep learning module, it's identifying the object in the image, getting a class or category, and it's aggregating the data from the sensors with the data from the image, with the label. And they are put together, and this is a more or less a valid observation. So I will start, we have to start this, to put this system online or on, and let's see what happens. The systems, the modules are synchronizing and the data is broadcasted, and the data are broadcasted from the IoT to the left part, to the server. What do we have here? We have data from the sensors. And the green part is the timestamp, because we want to aggregate this data by the timestamp. Which images was captured in the same time we have this set of data from the sensors. This is the idea. And the predicted source, it's right next to this green area. And we can decide to keep this information or not. If the data are not valid, they are not matching by the timestamp, we will get some red readings. We will see in a bit. First, we have nothing in front of the camera, and for that reason, the system is detecting this is daylight, not flashlight, not lighter, not anything else from our categories. So it's daylight. Let's read more. Okay, we have now a red line. This is because the data are unsynchronized. I'm supposing this is invalid. So the image captured was sent too late, and it's not good for our data. It's not reliable. So we can decide here which data we want to keep. As we can see here, I'm only supervising. I'm waiting for data to get labeled by using AI. I'm not doing my label myself, reading the values here. Actually, it's horrible to do this because, as I said before, our brain is not. We have only a few columns, but what about if we have 10 or 20 features? It's hard to comprehend. It's impossible. But still, deep learning is fine. So then I I put here a lighter. Now we expect to have some lighter data captured here. And then let's see, maybe we can save the data into a CSV file. And then let's see the flashlight. We can get some flashlight data as well. But you got the point. We are simply getting more and more data labeled. So we are getting our data labeled. Let's go further. This is the smart labeling because we are relying on the deep learning model. But as I said at the beginning of this talk, we might want to do the pre-labeling, and that's not involving artificial intelligence. We are simply selecting by hand which category we plan to get data for. So let's see, we are selecting, for example, the lighter, anything. Okay, let's see what we decided. So it's a, I guess it's a flashlight. And now we start. We have always here flashlight because we pre-selected in the right part. So now, in the same time, we get the data labeled. At some point, we have enough data. Now we can try to validate if our data is good enough by simulating a machine learning building process. Okay, let's wait a little. Let's push that button, validate, and let's wait for the code to be built. So we got a model which we trained with our new data, and the micro accuracy is 78% and macro accuracy is 75%. Good enough because, frankly, we have little data, too little data, but it's good enough. Easily we can get over 95% if we get enough data. Okay, that's the idea, and the demo finishes here. And let's get back to our presentation and jump to the conclusions. The application used for this demo, I think I told you before, it won the third place at Virtual ML.NET Hackathon a few months ago. And the source code, it's available on GitHub under my profile. It's called Smart Labeling. For academic purposes, we see a lot of examples from different areas of AI or AI plus IoT. But in real life, the most interesting solutions are those combining different types of machine learning and deep learning. Imagination is the limit, of course. Our mission is to make our lives easier. So one approach is to remove the redundant human work. Using image classification to label analytical data in datasets is a simple way to automate the labeling. I'm not saying it's easy from the IoT perspective, because you cannot have something pre-built. You have to adapt for your scenario. But it's cheap and it's performant. It's very time-saving. I mean, human work time-saving. Well, this is the idea, and the goal for my talk to show you how we can do the smart labeling.